Okay, so these are the notes for physics 10.1 through 10.6. And as we go through and look at the stuff that we're going to be covering here, we're starting with this concept of different phases of matter. We know that matter can be in a solid form, liquid form, and a gas form. And there are some other versions, such as plasma and liquid crystals. But for the most part, we're going to focus on the three main types, especially with what we're working with here in Chapter 10. And so as we look at some of the information we want to know about material, we recognize that different materials will have a specific density given that type of material. So gold has a density, no matter how much gold you have, in its standard form of like a solid form of gold, it's going to have a specific density. And so we need to understand what density is and how we calculate it. Density, which we use the Greek letter rho, equals the mass of an object divided by its volume. And therefore, it uses units of mass would be kilograms, and volume would be meters cubed. So it's kilograms per cubic meter, or per meter cubed. Now that information is in OneNote. It is in the text on page 256 of the textbook itself. You see right here, page 256, we actually have our table of different densities of different substances that we are going to commonly use for answering questions. So that's there as a resource if you need to go and look. For instance, the density of water at 4 degrees Celsius, the standard water temperature that we're going to look at, it turns out to be 1,000 kilograms per cubic meter. And we can look at things like copper, which is 8,900, or 8.9 times 10 to the third. So we have those densities there, which is really helpful. The second thing that we talk about with respect to density is what we call specific gravity. Specific gravity is really just a comparison of things against water. And the way we do that is we just take the density of an object or a substance, and we're going to divide it by the density of water, which we know the density of water is 1,000. And so if we take the density of steel, for instance, it's 7.8 E3, and the density of water is 1.0 E3. Well, these E3s are actually going to cancel, and anything divided by 1 is itself. So the specific gravity of, this was steel, is 7.8, which it doesn't have a unit. It's just a comparison or a ratio, which means it's 7.8 times more dense than water. And that's really what we're looking at. This is definitely not going to float under normal circumstance. We have to shape it to give it the ability to float. Okay, after we get through this idea of density, we're going to understand eventually that density has something significant to do with pressure. And so real quick, we're going to go ahead and kind of scoot that over, and we're going to start talking about our next big idea, which is what we mean by pressure. Okay. Ooh, that's a funny looking peak. Let's change that so it doesn't look so funny. There you go. P equals force over area. And so pressure is going to be measured in units of newtons per meter squared. You know, you can put a lot of weight on something and that's going to create pressure, but more important than the weight is actually the area. If you think about it, a small radius of a circle, it's going to make this pressure go up really fast because the radius is squared. So the area matters just as much as the force, but it's sometimes that area is in a circle form, and then that radius is going to determine a lot about the pressure. There are a couple of other units. A newton per meter squared, we've actually named this unit what's called a Pascal. It's a PA. It's named after Pascal, who did so much work with different formulas and deriving different things with respect to pressure. So we name it after him. Both of these units are exactly the same things in terms of science and numeric value. There are a couple of other pressure values or conversions we're going to want to know. For instance, sometimes we'll talk about an atmosphere of air pressure. Well, 1 atm, or 1 atmosphere, is equal to 1.013 E5 times 10 to the 5th newtons per meter squared, or pascals. The other one that gets used quite often is millimeters of mercury, and 1 millimeter of mercury, that's just an old standard way of measuring it, still used pretty often in medical fields. That comes out to be 133 newtons per meter squared. So those are a couple of conversions you might use when you talk about pressure. But then we've got to talk about Pascal's principle, which is a really cool principle. We use it in hydraulics and in all kinds of stuff today. Pascal's principle tells us that if we have a closed system, okay, where there's no leaks of our fluid, and this is what we're going to call a non-compressible fluid. So you can imagine there's a piston here on each side, okay? All right, so we've got our piston on each side, and this is all filled with fluid, okay? If I apply a force down there, okay, call that force in, it's going to increase the pressure inside of my device. It's going to apply a pressure into this fluid, and because it's non-compressible, it's going to push with the same pressure up over on this side. So whatever pressure increase I try to create, it's going to have that back side pressure as well, and so it's going to apply a force out. Now the pressure, the force in is not going to equal the force out, because the continuous piece is the pressure of the fluid. That's the constant. So because P in is equal to P out, if we think about pressure as being force over area, this would be F in over A in equals F out over A out. Now we use this all the time in mechanized processes, from your power steering to your braking to the crane, how the crane uses hydraulics. All of this stuff operates under this principle. The reason this matters so much is if you have a small number like 1 Newton going in, but your area is 0.5 meters squared. I'm just going to use some big numbers here, just bear with me. But on the back side, I say quadruple the area and make it 2 meters squared down here. The F, to make this still a balanced equation, 1 over a half is 2, okay, yep. And so over here, because I have a 2 here, I would have to have 4 newtons in order to get 2 on the right side. So if you think about cross multiplying, if you will. But what this tells us is that with very little force, I can get a lot of bang for my buck. Getting to 4 newtons of force, that is a 4, there's a question mark, but getting to 4 newtons of force out of a 1 newton of force, this is like a simple machine, but way efficient. We're able to quadruple or even 10 times our force just by changing the ratio of the areas. All right, the last thing, so that's Pascal's principle. The last thing we need to talk about is that as you go into a fluid, any fluid, okay, the further down you go, the more fluid there is above you. If you think about it in layers, okay? And as I keep going down, there's more and more water or some other fluid above me. It's going to continue to increase pressure all around me. Okay, so boom, boom, boom. And so that pressure, you know, it starts out pretty small, not a lot, and then it just gets bigger and bigger and bigger as I go down. So there must be a relationship between pressure and the depth, or we'll call it the height, that I am inside of a substance. Well, it turns out that the pressure can be equated to, okay, the density of the fluid times gravity times your height. Now when we talk about your height, okay, you have to understand this is kind of more of a depth that you need to think about, okay? Because the further down I go, the more pressure there would be. So this would be H2, this would be H1. It's important to understand that H2 is greater than H1. Yeah, it's lower, but we're looking at how is it measured from the edge of the surface, okay? So this also works for us here on Earth. When we talk about sitting underneath the atmosphere, you know, right now at sea level, there'd be the whole atmosphere above me. As I go up, there's less atmosphere above me, and so my H would decrease, which it seems kind of strange, but think of H as a depth, not a height. But the key here is that there is a pressure difference between the first case and the second case. And so this change in pressure The only thing that changes from one spot to the other is the height. And so we can talk about the pressure difference between these two places as rho times G times delta H. Now, this is really helpful with one understanding. Technically, most fluids will compress under extreme pressure as you go deeper and deeper. The bottom of the ocean has more dense water, or water that is more dense than the water at the top of the ocean. But that's a pretty big difference in height. Most of the problems that we look at and the things that we're going to consider are going to be within close enough height-wise that there's not a significant difference in the density of the fluid. It is possible, again, as you go towards space, the density of the air gets smaller, it gets less. So theoretically, we could get to a place where this becomes more of a concern. But initially, that pressure difference is going to be really held by the height difference or the depth difference. I hope that's enough to kind of give you what you need to know to be successful. Thanks. Bye.